Kelvin's age of the Earth was finally disproven at the end of the 19th century with a discovery made in the Paris lab of Henri Becquerel and Marie Curie. Curie is one of the great scientists of her and all time. She remains the only person to have won Nobel Prizes in two separate scientific disciplines, one in physics in 1903 and one in chemistry in 1911. The one in 1903 was for her discovery of radioactivity. The concept of isotopes wasn't really understood when Becquerel and Curie were doing their work, but it's easier to interpret their work with reference to the isotopes. Remember, an isotope is a variety of an element with a specific number of neutrons in its nucleus. Lithium, for example, always has 3 protons, but it can have 3, 4, or 5 neutrons, producing 3 different isotopes: lithium-6, lithium-7, and lithium-8. Some isotopes are unstable and spontaneously decompose, producing another isotope in the process. The initial isotope is called the parent, and the one produced is called the daughter. In the process of alpha decay, which is shown here, the decomposition occurs when the parent isotope ejects an alpha particle, which is nothing more than a helium nucleus, 2 protons and 2 neutrons packed together. The key property of radioactive decay that ultimately killed Kelvin's estimate for the age of the Earth is that the decomposition of the parent isotope is always associated with the production of heat. Remember that Kelvin's model assumed that the Earth was originally a hot sphere and has been undergoing cooling ever since with no other additions of heat. Radioactive decay, however, has been providing a constant supply of heat, invalidating Kelvin's assumptions and his conclusions. The Earth must be older than Kelvin thought. The radioactive decay that occurs with the ejection of an alpha particle is called alpha decay, but elements can also transform by what's called beta decay. In beta decay, a neutron transforms into a proton or vice versa. The most common one is where a neutron transforms into a proton and in the process ejects an electron and a high-energy neutrino. It's also possible for a proton to absorb an electron and transform into a neutron. Beta decay is how carbon-14 decays to nitrogen-14, one of the most well-known radioactive decay transformations. By converting a neutron into a proton, carbon transforms into nitrogen, but since the total number of neutrons plus protons stays the same, the atomic mass doesn't change. It's still 14. This plot makes some important points about isotopes. What's plotted is the number of neutrons on the x-axis versus the number of protons on the y-axis. The line N for neutrons equals Z for protons is for isotopes that have equal numbers of neutrons and protons. And you can see that hardly any of them do. Only some of the very light elements can have equal numbers of neutrons and protons, but most isotopes have an excess of neutrons. Also notice that in general, an element has several different isotopes. For example, calcium, which has 20 protons, has 7 different isotopes ranging from calcium-39, in which there's actually 1 fewer neutron than protons, all the way to calcium-48. Notice that calcium-41 and calcium-47 don't occur. Also, the color coding corresponds to whether or not the isotope is stable or not, with green ones being stable. In general, the unstable isotopes occur at the extremes of the range, with either a relatively large or relatively small number of neutrons. Radioactive decay can be described with some pretty simple mathematics. The key idea is that the rate of decay is proportional to the number of atoms. The more atoms, the faster the decay. We could write this using calculus like this, with dN dt equal to the rate of decay and alpha being the constant of proportionality. Alpha determines how fast an isotope decays. When alpha is large, the isotope decays rapidly. When alpha is small, it decays slowly. If we integrate this differential equation, we can derive an expression for the number of atoms of the parent isotope as a function of time, which is shown in yellow. In this equation, n sub 0 represents the initial number of parent isotopes. If you're like most people, it's easier to see what's going on if we graph the equation. Here's what it looks like. Time is on the x-axis, and the percentage of parent atoms remaining is shown on the y-axis. At time 0, 100% of the parent is there, but as time goes on, less and less remains. The time steps on the x-axis aren't arbitrary. They're carefully chosen so that exactly 1/2 of the original remains after one increment. For example, from increment 0 to increment 1, the amount of parent goes from 100% to 50%. From increment 1 to increment 2, it goes from 50% to 25%, and so on. This period of time when half of the original parent decays to daughter is called the half-life. When the decay constant alpha is large, the half-life is small, and vice versa. This is because rapid decay, which is caused by a large alpha, causes a small half-life. Also notice that because there's a one-to-one correspondence between the parents that decay and the daughters that are born, we can also plot the increase in daughter isotopes with time on the same graph. At any given time, the number of parents plus daughters must sum to the original number of atoms, or on this plot, 100%. At this point, it might occur to you that if we can measure the number of parents and daughters, we ought to be able to determine how long the parent has been decaying, which we take to be the age of the rock. In other words, the ratio of parent to daughter correlates with age. For example, when the ratio is 1:1, exactly one half-life must have passed, and if we know the value of the half-life, we ought to know the age of the rock. In fact, it's not quite that simple, but the basic idea is intact. Becquerel and Curie's discovery not only shot down Kelvin's age of the Earth, but it also provided a means by which geologists could calculate it using radioactive decay. That will be the subject of another slideshow. Geologists, in fact, now routinely use radioactive decay to measure the age of rocks. The most useful isotopes are those that have long half-lives because rocks, like Hutton predicted, tend to be pretty old. These are the most common ones used to measure the age of rocks, and you'll notice that most have extremely long half-lives, with the exception of carbon-14, which has a very short half-life of less than 6,000 years. As a result, carbon-14 is only useful for dating very young samples because for old samples there simply isn't any parent left to measure. In contrast, lutetium-176 can only be used to date the very oldest rocks on Earth because for anything younger there won't have been enough daughter hafnium produced to measure because the half-life is just so darn long. There's one more detail that needs to be mentioned about radioactive decay. Many isotopes decay as part of a long chain because the daughters themselves are unstable isotopes. For example, uranium-238 decays to thorium-234, which in turn decays to polonium-234, which goes to uranium-234, etc. The chain doesn't stop until it reaches lead-206, which finally is stable. This looks hopelessly complicated, but like many chains, it can be simplified. Many of the steps in the chain are extremely rapid, and in fact only one step, the very first one of uranium-238 to thorium-234, is significant because it has a very, very long half-life of 4.67 billion years. The rest of the steps are, from the perspective of this first step, nearly instantaneous. As a result, after thorium-234 is produced, the isotopes cascade down the chain incredibly rapidly all the way to lead-206. The production of thorium-234 is the bottleneck, and the transformation that determines the rate at which the final isotope, lead-206, is produced all depends on the transformation to thorium-234. As a result, we can think of this as if uranium-238 was directly transforming to lead-206 with a half-life of 4.67 billion years. In fact, the half-life of 4.67 billion years, it's what's shown on this table for uranium-238, even though there are many, many intermediate steps that aren't shown.